Hello, students. I told you in the video before that I should do some example and then maybe go further on. Now let me first do the example. I have the following integral x plus 1 and I am defining it by some square root of x squared plus 2x plus 3, and then you have there to take the square root of it. So the x, and then we can also do some bounds, for instance, from 1 to 0 or something like that. Okay. Now, first of all, I see if I go with my x from 0 to 1, then the number being where you have to take the square root of is always positive, so that gives no problems. And so I think that integral will exist. That is no problem. But then, yeah, it is always a little bit from what to do, but what can you do? Um, I see here x plus 1 and I see here x squared plus 2x, and that looks very much that you can maybe do the following. If you have x plus 1 squared, what do we get then? We have then x squared plus 2x plus 1, and then you see that x squared plus 2x you see back. So I think that I can take as for the substitution of the new variable that I can take u is equal to x plus 1. So I think that I will try to substitute this substitution, and then I will see what goes on. If I have then u squared, I have x squared plus 2x plus 1, but I see here an plus 3. So I see that you have u squared, and if I add 2 to it, then you have the x squared plus 2x plus 1 plus 2, and that gives me exactly what is staying there below the square root. So that is okay. So I have u squared plus 2 below the square root. Okay. So I think this goes well. And I see also that the du term, yes, what becomes the du term? That becomes equal to the x in this case. And then I don't know if that is a nice way to work with. So I am asking myself from what to do. I think this is not a nice way, because then what do you get out of that integral? You have your x plus 1. What can we then write? Yeah, that becomes the x plus 1 becomes the yes, and what do we have then? I am now asking myself, what can I do? I think this is not a nice thing to do. So this is some try, but no, it doesn't. It is not what I want. What to do then? This doesn't go well. You have here x plus 1, and your x plus 1 becomes the u, but what do we get then for integral? The x plus 1, so that becomes the u term, the dx is equal to the du term, and we have that integral that becomes u squared plus 2, and then taking the square root of it. Now, and this is, yeah, you can do it, that is no problem, but sometimes you want to do it at once. And so what can we also try to do? Maybe we can also take for the u that x squared plus 2x plus 3. And maybe this is also a possibility, because what is then the du term? Now you have to differentiate the expression. Here you get 2 times x plus 2, and there you see that you get 2, sorry, and then I'm forgotten here to write down the dx term, and you dx, and here I see 2 times x plus 1 dx, and then I see here the x plus 1 dx back, that I see here also in the integral there, so I see also that x plus 1 times dx back. So I think maybe this is an, I will not say better choice, but this is maybe a choice you can also use to calculate that integral. Now let's try. What do we have then? If I take this u, the lower boundary, the x starts in 0, and if you fill in x is 0 there, you see that the u becomes equal to 3. The upper boundary for the x was taken to 1, and that gives you for the u, now fill in 1 everywhere, and you have 1 plus 2 plus 3, that gives you 6. And so okay, so let me give it a name I2. Then I have not to rewrite that complete integral, and I2 becomes then the integral, and I'm writing it over in the new variable u. Now the lower boundary becomes 3, upper boundary becomes 6. The x plus 1 term, the x plus 1 dx term becomes 1 over t times du, and we have here below, well, what do we get here below? There we get the square root of u. Yes, I think this one is, I have now rewritten the complete expression to this one here. Okay, and I can go on because if you are here, you are dividing by some square root, and if you take the primitive function of u, you get the square root of it. So I have here the integral from 3 to 6, and then I have the square root of u, and I think I have to multiply it by 2, so I get 2 divided by 2 times the, sorry, and now I'm stupid. I want to calculate the primitive function of it. So, and I have here just, I want to do now something else, I don't know what. You have here the primitive function becomes the square root of u, because if you differentiate it, you can well 1 over 2 times and then minus 1 over 2, so you are dividing by the square root, okay, and that between the boundaries 3 and 6, and so we have here the square root of 6 minus the square root of 3, if you calculate that value. Now, you can do the same in certain sense what we tried first, that you can do, because then you can take another variable, for instance, and so you see that you can, that there is not just one way to solve it. There are a lot of ways to try and do, and sometimes it goes well and sometimes it goes wrong. This one here, yeah, we had first. Now what can we also do? Now we can also take a new variable v, and for instance that we can take to the u squared. Then the dv becomes 2 times u du. And what do you see? You have a term u du, and I see here also back. And so I see that I get some integral of 1 over 2 times dv, and then I have here, I get v plus 2, and you have to take the square root of it. And now, and then you can go on with your primitive function, and you have, for the primitive function, you get v plus the square root of 2 plus some constant. But now, if you now want to calculate that integral, you have to go back to the x term, and then you have to see from, oh, now what was v? V was equal to u squared, and what did we take there for the u? There, well, that was the x plus 1 squared, and so you have here, you see for the that you get x plus 1 squared plus 2, take the square root of it plus some constant. And if you now fill in the upper boundary and the lower boundary of the x variables, and the lower boundary for the x was 0. Now, what do you get for the lower boundary? You get the square root 3, and if the x is equal to 1, we get the square root of 6, and you get the same expression as we have for the solution already of the integral, and that is the expression of the square root of 6 minus the square root of 3. So you see with some other way, and here we have now used two substitutions. And so you see that you can do it on very much ways, and not only one way. And so you can try and see if you get something out of it or not. And sometimes it goes well, sometimes it goes not. You see. Okay. Now I want to do. I want to start with chapter 6.1, and that is the partial integration. Now, what is the idea behind it? Now, with the substitution, I use the composition of two functions, and here I use the rule of multiplication of two functions. If you have two functions, if you multiply them together and you want to take the derivative of it, you know that you have that rule of the derivative of f times g plus f times the derivative of g. Okay, and what can we now do with that one here? Now, for instance, if somebody should ask you the integral of the derivative of f times g dx, then we are using this part here. Now, what can we then do? Then we can write here, this is equal to the integral of, and then you have the derivative of that product of two functions minus the integral of f times the derivative of g. And this part you put to the other side, and you get a minus sign, and okay, and now you have a primitive function of the derivative here. You are taking derivative and you are integrating it. So what do we get out of it? Here you get the function f times g minus derivative of f times the derivative of g. And here you have your, in certain sense, the partial integration, and you have then here around the brackets you have to put the the boundaries where you are integrating. So from that rule of the multiplication rule of differentiation, you can find that rule of the partial integration. And here staying the primitive function of the derivative of f times g is equal to now f times g, and then you have minus the integral of f times the derivative of g. So be careful. And that is the same way you have you need to to try something and then look if it goes well and if you get something out of it which works or not. For instance, the integral of x squared times the cosine of x dx. Now, I don't know directly what should come out of it. I have really no idea, but it should be nice if I could get that x squared, I could get the power lower than to beneath. If I get it to 1 or if I get it to 0, that should be very nice. And um, and so what do you see? And I can get it lower by differentiating it. Now and then I look to that rule of the partial integration, and then I think to myself, what can I use? Now what do you see? You you have you start with the derivative of f times g, and then you get the derivative of the g. And so I think that a way to do is maybe that we take for this function that we take it equal to g, and that this one that we take the derivative of f, and then we try to use that rule of partial integration. Now what do you get? You get some brackets, and then you get f of g times f. Now the g is the x squared, that nothing changes, but you have to take the primitive function of the f of the cosine, and that becomes the minus sine of x. That is the primitive function of the cosine. And then we have to subtract some integral. And how looks that one? Now you start with g times the derivative of f, and then you should get the derivative of g times f. Now and then the derivative of g becomes 2 times x, that's okay, and the primitive function of that and f was equal to minus the sine of x dx. And so if you write it out, you see that you get minus x squared times the sine of x, and then be careful with the minus 2 times, and then we have plus the integral of 2x times the sine of x dx. And so you see that you have already the power of x one lower, but we want to still, I want to get it once lower again. So I use again the partial integration. Now what should we do? Again, I think that we will use this one again as the f, and this one the sine of x that we take as the derivative. And then what do we have? Now the first part between the brackets I let stay, I nothing do with it, and then I plus, and then I use again that partial integration. So I have the first part is g times f, so that becomes 2 times x, and what is the derivative? What will give you the derivative as the sine if you differentiate that function? I think the cosine. So yes, and then I have done it wrong, and you see that I have done it wrong because the derivative of the sine is the cosine. What stupid guy I am. So I have here a plus, and here also a plus term, and here I have, and you see that I also make errors. Just like you, I will also make errors. And now I have to be careful. Now I need that minus sign, because now I have minus the cosine of x, because the derivative of the cosine is the minus sign, and with this minus sign before you get the sine of x. And here you have your g, there you have your f, and then you have to subtract almost the same expression, but then with the derivative of g times f. Now the derivative of g, that becomes 2, and the f that was equal to minus the cosine of x. So, and here you see your g and your f, and here you see your derivative of g, and here you see your f. Now, that gives me minus x squared times the sine of x, and I have minus 2x times the cosine of x. Okay, and then I have plus 2 times the integral of the cosine of x dx, and and if you integrate the cosine you get minus sine, and so we have here for the primitive function minus x squared times the sine of x minus 2x times the cosine of x, and I have the plus the sine of x, sorry, 2 times the sine of x, and be careful, don't forget that constant. So I think this one will be the good one. And I will look again if I have not made some stupid error. The derivative of the sine is the cosine, that it goes well. Yes. Okay. And here you have minus 2x, yes. And if I, yes, and the derivative of the, that this goes well, minus minus, and you have here, if you take the derivative of the sine of x, you get the cosine of x, that's okay. So yeah, I think this one is the good one. Yes. Now, and so you see that you can try to, with that partial integration, and so that we use again that rule of partial integration. So you have the derivative of f times g dx becomes equal to f times g, and then minus the integral, let f stay, and you have the derivative of g dx. So this is your rule of your partial integration, and that has to do with the rule of the derivative of f times g. Okay, now um, let's see what to do. I think that I now stop with this partial integration, and the next video I will do more examples partial integration. So in this lecture we have used that rule of substitution. So if you have that f u du, now if you have fill in for the u a function which depends on x, then you have the du becomes equal to the derivative of g dx, and then we have here nothing else as the integral of the g of x times the derivative of g of x dx. So this is your substitution rule. Important, certainly it will be asked on it. Substitution, important, and most of the time, yeah, we will use it from the right hand side to the left hand side, and you have to find your u, but you will see how you come to it. And in that example above, here you see the partial integration. And with partial integration, yeah, you work from the left hand side to the right hand side, and you always try, you hope that this integral, you will try, yeah, to make it easier. That is what you try to do, but sometimes it will not always go as it will not always go, and then you have to change. Then you can also do the integral of the derivative of g times f. You can use both things. And you hope, and in certain sense, with the substitution, you hope always that the integral on the left hand side is easier. That is most of the time what you try to do. But yeah, that is a trying.